taps into something deeply intuitive.
Mm-hmm.
If every particle is at a distinct location in space-time, right, and it experiences a unique configuration of physical fields just because of that location,
Yeah.
well, doesn't that make every single particle unique?
Yeah. And it feels right, doesn't it? It completely matches our everyday experience with, bigger objects.
Exactly. Like my coffee mug here and your screen over there, they're definitely different objects, and partly that's because they're in different places. They're feeling slightly different gravity, maybe different light hitting them.
Different electromagnetic field, sure. Where something is and what's influencing it there, that absolutely defines its immediate reality for us. Location equals uniqueness feels like, well, common sense.
It totally does.
Right.
But, common sense on our scale, it doesn't always map neatly onto the fundamental level, does it? The world of tiny particles?
Not always, no. Things get much weirder down there.
So what does modern physics, the physics describing those really small things, actually say about this idea? Does uniqueness really come down to just space-time location? That's kind of our mission for this deep dive.
Right. We'll take that intuitive idea and really test it against how physics thinking has evolved. We'll look at the classical view, then relativity, quantum mechanics.
And finally, quantum field theory, the current picture.
Exactly. And we'll see how this seemingly simple idea gets, well, pretty much turned on its head and then rebuilt in a completely different way.
Okay, so let's start way back. The classical picture. Newton's clockwork universe, deterministic, predictable. In that world, what is a particle? And who are the main players we're even talking about here?
Well, classically, you imagine a particle as just a tiny, indivisible point, like a billiard ball shrunk down infinitely small. And it has certain built-in properties that don't change its mass, its electric charge. And the players, the fundamental bits we're trying to describe ultimately, are things like electrons, quarks, the stuff matter's made of, and also the force carriers, like photons. Classically, you treat each one as one of these little points.
Right. And its whole story, classically, is determined by knowing its exact position and its exact momentum at one moment.
Precisely. If you know those and you know the forces, boom, you know its entire path through space and time. It's world line, we call it. That path is unique, hitting unique points in space-time. That's the classical unique location.
Okay, but interactions, they don't just happen instantly across space. That was a big realization.
Right, that was a huge shift. Interactions happen through fields. You can think of fields as these invisible influences filling space. A charge creates an electric field, a mass creates a gravitational field, and another particle doesn't feel the source directly from far away. It feels the field right where it is.
Got it. And Maxwell's equations were key for electricity and magnetism. What's important about them for our question?
Well, Maxwell unified electricity and magnetism into one electromagnetic field. That was huge. But critically, his equations showed something dynamic. A changing electric field makes a magnetic field.
Okay.
And a changing magnetic field makes an electric field. They kind of bootstrap each other.
Ah, right. And that's how light works.
Exactly. That dynamic interplay allows these self-sustaining waves, electromagnetic waves, light, to travel through the field itself.
So fields are everywhere. They're dynamic. If our classical point particle is at a unique spot, does it feel a unique field pattern there?
Yes, definitely, in the classical setup. Two main reasons. First, something called the principle of superposition. Basically, because Maxwell's equations are linear, the total field at any point is just the vector sum of the fields from every single source in the universe, every charge, everywhere.
Wow. Okay, so the field value right here is like a fingerprint of everything else out there, all added up at this one specific point.
You got it. It's determined globally. And second, there's a mathematical proof. The electromagnetism uniqueness theorem, which says that if you know all the sources and the conditions at the boundaries, there's only one possible solution for the electromagnetic field everywhere.
So classically, the listener's premise holds up perfectly. Unique path, unique points, unique field value sampled at each point. Uniqueness comes from the outside, from its location.
That's the classical story. Location is king. Bucho. Exactly. There's a crack. A really profound crack appears when you look too closely at that point particle idea itself.
The self-interaction problem.
Exactly. If an electron, say, is truly a mathematical point with zero size, the electric field it creates becomes infinitely strong at its own location.
Infinite field. That sounds bad.
It is. It implies infinite energy stored in the field, and the force of the particle on itself becomes undefined. It blows up. It tells us the model is breaking down, that a point particle can't be the full story, especially for those fundamental guys like electrons and quarks works.
Okay, so the classical picture, while elegant, kind of trips over its own feet at the smallest scales, which sets the stage nicely for the relativistic shift, right? Einstein shaking things up.
Big time. First, special relativity fundamentally changed how we see space and time. No longer separate things, but a unified, four-dimensional space-time.
Right, space-time. Events are points with four coordinates, time plus XYZ for space.
Yep. And a particle's history, its world line, is its path through this 4D space-time.
And crucially, even if different observers disagree on distances or time separately, they all agree on something called the space-time interval between two events.
That's the key invariant quantity. It gives an objective measure of separation between events and space-time. So space-time points become the objective locations for events. This actually reinforces the classical idea of a unique path through objective points.
But then Einstein went further with general relativity and redid gravity completely.
He did. Gravity isn't a force anymore in GR. It is the curvature of space-time itself. Mass and energy warp space-time around them.
And things moving through that space-time just follow the curves, the straightest paths possible in that curved geometry, geodicas.
Exactly. Like John Wheeler famously said, matter tells space-time how to curve, and space-time tells matter how to move.
Okay. And the Einstein field equations connect the matter and energy to the curvature. How does uniqueness work for the gravitational field, which is now this space-time geometry?
Well, the Einstein field equations are much nastier than Maxwell's. They're nonlinear, super hard to solve. But the principle holds. For a given distribution of mass and energy, the solution for the space-time geometry, the metric tensor, is unique. Well, mostly.
Mostly. What's the catch?
The catch is our choice of coordinates, like using different map projections for the Earth. You can describe the same curved surface using different coordinate grids.
Ah, okay. That's called gauge freedom, right?
Exactly. So the specific numbers in the metric tensor might look different depending on the coordinates you choose, but the intrinsic curvature, the actual physical warping of space-time at a point, that is uniquely determined by all the mass and energy.
Got it. So different descriptions, same underlying reality. So relativity actually deepens the original premise in a way. Unique world line, unique space-time points, unique local space-time curvature experience there.
Precisely, and that local curvature is linked to the global arrangement of mass and energy across the cosmos, tying the local experience to the whole universe in this deterministic way. It's a very holistic picture.
Okay, so classical physics, relativity. They both seem to support the idea of uniqueness coming from location, albeit in increasingly complex ways. But now we hit the wall. Quantum mechanics. This is where it really changes, isn't it?
Oh, yeah. This is the earthquake. Quantum mechanics just fundamentally dismantles the core assumptions of that classical picture, especially location and identity.
And the first big wrecking ball is the Heisenberg uncertainty principle, right?
Definitely. HUP. It states there's a fundamental limit, an inherent fuzziness to how well you can know certain pairs of properties at the same time. The classic pair is position and momentum.
You can know where it is or where it's going, but not both perfectly precisely.
Exactly. And it's not just that our tools are bad. It's baked into reality. You cannot simultaneously know the exact position and the exact momentum of a particle.
Which means the whole idea of a particle having a precise location and following a definite path, a world line, just dissolves.
It completely breaks down. If you can't know both where it is and where it's going with certainty, the concept of a single, unique trajectory through space-time points becomes meaningless at this level.
Whoa. Okay, so if it doesn't have a precise location, how on earth do we describe it?
We use the wave function, psi. Instead of being at a point, the particle is described by this mathematical object that spreads out over a region of space. It represents a superposition of possibilities, a sort of probabilistic cloud.
The cloud. And the density of the cloud tells you where you're likely to find it.
Pretty much. The Born interpretation says the square of the wave function's amplitude at any point gives the probability density of finding the particle right there if you were to perform a measurement.
If you look for it.
Right. The act of measurement seems to force it to choose a location. We say the wave function collapses. But before you measure, it's fundamentally smeared out, delocalized.
And that must change how it interacts with fields, too. It's not just sampling the field at one point anymore.
Exactly. It interacts probabilistically across the whole region where its wave function exists. The interaction itself becomes non-local in a sense.
Okay, so goodbye precise location. But quantum mechanics doesn't stop there, right? It messes with the idea of identity, too.
Oh, absolutely. This is maybe even weirder. It's the principle of quantum indistinguishability. It says that all fundamental particles of the exact same type, all electrons are electrons, all photons are perfectly, utterly, identically the same. Not just similar, but indistinguishable.
What does that mean in practice? Like if two electrons bump into each other?
Yeah. In classical physics, you could imagine labeling them electron A and electron B and tracking which one went where after the collision. In quantum mechanics, if their wave functions overlap, that question, which one is A and which one is B afterwards, becomes literally meaningless.
You can't tell them apart, even in principle. Their individual histories just blend together.
Precisely. You lose the ability to track individual identities or assign unique trajectories once they interact or overlap. There are rules about how the combined wave function must behave because of this identity. Symmetry rules for bosons, anti-symmetry for fermions. But the core point is, uniqueness can't be tied to a traceable path if you can't even uniquely assign the path to a specific particle.
Wow. Okay, so quantum mechanics just devastates the original premise.
Yeah.
No definite location, no unique trajectory, not even a persistent individual identity in the classical sense.
Yeah.
So if uniqueness isn't in space-time location or history, where is it? What makes one electron different from another in any situation?
Right. That's the big question quantum mechanics leaves us with. And the answer comes from our most modern picture, the synthesis of quantum mechanics and relativity, quantum field theory, or QFT.
QFT. Okay, how does QFT change the game?
It introduces a fundamental shift in ontology in what we think is real. In QFT, the fundamental things aren't particles anymore. They're fields, quantum fields.
The fields again, like the electromagnetic field.
Exactly like that, but more fundamental. There's an electron field permeating all of space-time, a quark field, a photon field, one for every type of fundamental particle we know. These fields are the basic reality.
Okay, so then what are the particles, like electrons and photons?
Particles are excitations of these fields. Think of the field like a calm ocean, the vacuum state. A particle is like a wave, a ripple, a quantized vibration or excitation in that ocean carrying a discrete amount of energy.
Ah, so the field is the underlying thing, and the particle is just a temporary blip on it.
That's the picture. It beautifully merges the wave nature, the field, and the particle nature, the discrete excitation.
Okay, fields are fundamental, particles are excitations, but we still have the question. If location doesn't grant uniqueness, what does? Especially for identical field excitations.
Now we get to the heart of it in QFT, especially for the matter particles, the fermions, electrons, quarks, neutrinos. Their uniqueness comes not from space-time coordinates, but from something else entirely, their quantum state. And the rule that enforces this uniqueness is the Pauli Exclusion Principle.
PEP. Okay, heard of that. What does it state, clearly?
The Pauli Exclusion Principle states, very simply, that no two identical fermions can occupy the exact same quantum state simultaneously within the same system.
Okay, identical fermions, like two electrons. But what exactly is a quantum state in this context?
A quantum state is basically the set of properties that completely defines the particle's condition within that system. It's described by a set of quantum numbers. For an electron in an atom, for example, these numbers specify its energy level, how much angular momentum it has, the orientation of that angular momentum, and its intrinsic angular momentum, its spin.
So it's like a unique address, but not in physical space. It's an address in possibility space, an abstract space of allowed properties.
Exactly. It's an address in what physicists call Hilbert space, the space of all possible quantum states. The PAP guarantees that each identical fermion in a system gets its own unique address in this abstract space. If two electrons are in the same atom, they must differ in at least one of these quantum numbers. Maybe they're in different energy shells, or if they're in the same shell, maybe they have different spin orientations.
So uniqueness is guaranteed by having a unique set of these quantum numbers.
Precisely. And crucially, the PEP isn't just some passive bookkeeping rule. It's an active principle. It's doing work. It's shaping reality.
Active. How is it active? What does it do?
It's the fundamental reason matter is stable and structured. Think about it. If there were no exclusion principle, all the electrons in an atom would just cascade down into the lowest possible energy state, piling on top of each other.
Okay, yeah, that sounds like it would just collapse.
It would. But the PPP says, nope, only one electron per state. Or technically two if they have opposite spins. But the point is, states fill up. So electrons are forced to occupy higher and higher energy levels, creating the distinct electron shells we learn about in chemistry.
Ah, And those shells are what determine how atoms interact, how they form bonds, right?
Exactly. The structure of the periodic table, all of chemistry, the existence of complex molecules, the fact that you can't push your hand through a table, it all relies fundamentally on the Pauli Exclusion Principle, forcing electrons into unique quantum states. It mandates a kind of individuality that builds complexity.
That is really profound. So the classical uniqueness was passive, just what field value happened to be at your location. But this quantum uniqueness, enforced by PP, is actively building the world by forcing particles apart into different states.
You've got it. That's the modern understanding. When we interact with the world or make measurements in QFT, we cause these field excitations to momentarily appear localized, like particles at points. But their deep reality is, as excitations defined by their unique quantum state, a uniqueness protected and enforced for fermions by Pauli.
Okay, let's try and wrap this whole journey up then. We start with that very intuitive listener question. Is a particle unique just because of where it is in spacetime and the fields there?
And we saw that, well, classically and relativistically, that picture works pretty well as an approximation, especially at larger scales. You have unique paths, unique points, unique field values, unique space-time geometry, all conferring a kind of external uniqueness based on location.
Mm-hmm. But then quantum mechanics came along and really threw a spanner in the works. Uncertainty destroyed precise location and paths, and indistinguishability dissolved the idea of tracking individual particle identities.
Right. It completely undermined the foundations of location-based uniqueness, leaving us searching for a new source.
And quantum field theory delivered that source.
Yeah, QFT gives us the modern answer, which is kind of a no but.
No, uniqueness doesn't fundamentally come from space-time location for these identical particles. But it does exist, and it comes from the abstract space of quantum states, enforced for fermions by the Pauli Exclusion Principle.
Particles are field excitations, and their individuality, their uniqueness within a system, is defined by that unique set of quantum numbers, that quantum state address.
Exactly, and that's the crucial takeaway for you, the listener. This quantum uniqueness isn't just some label. It's not passive. It's an active architect. The PEP is the reason matter doesn't collapse, the reason we have chemistry, structure, complexity.
The universe we see, stable and intricate, relies on this rule about abstract quantum states, not just where things happen to be.
It's a fundamentally different kind of uniqueness than the classical intuition suggests. So here's a final thought to leave you chewing on. Just consider that. An abstract rule, the Pauli Exclusion Principle, operating in an abstract space of quantum states, basically. A rule about identity and possibility dictates the concrete, tangible, physical structure of literally everything around us, from atoms to stars to us. How does that abstract instruction about not being in the same state translate into the solid, diverse reality we experience?
Yeah, how does that abstract rule about identity give rise to the very substance and variety of the physical world? That's something worth pondering.